Okay, so this is the last thing we did earlier today, this morning. I We start with a function and then define what a Riemann sum is, and then define it is the limit is that the the definite integral. Okay, so let's explore some more about this a definition of integral. Okay, so let's so let's start. Oh, right. Okay. Here we start with the uh, given a say a function looks like this one. Now the functions can be, or it may have also some discontinuity. Okay, so that's not necessarily everything above the x-axis, but say a and g. If we have x and y, so there's y equal f of x. Okay, so let's do this one. Uh, the for process, four step. One is partitions in the interval. Okay, and two is you take a sample. And you say pick a sample. So compute area, calculate area. Uh, say pick a sample rectangle because it's rectangle. Uh, Calculate area. Third, sum of all the area of the rectangles. And then the last thing is take limit. Okay. The sum that you get from here is called Riemann sum. Riemann is a Swiss mathematicians in the 18th centuries. Okay, so let's do this one. Partitions. Partition means we divide this one. So step one, partitions is x0, x1, x2, x3. That and the last thing is that let's see the end, right end of the interval. Okay, so that's the our partitions. And all right, and we call this the delta is x and minus x I minus 1. Okay, so the length of each of this. Okay. And for partitions, we know how to measure size of partitions. The notations is that norm of P, like just like the norm of all factor is its notations. Okay, and it's defined as the minimum. So the smallest one will be the our measure of a partitions. Okay. Two, we pick a rectangle. So what we do here is that for each of this, right? And so let's pick a representative for each of these. So you have rectangles, many rectangles here. Partitions. And you have xi star is the representative of the subpartitions. Okay. The height will depend on the height of the functions, the height. All right. Now pick a sample. When you pick a sample, for example, like this, say the length is delta ix, okay? So that's the width, okay? And the height is determined by f of xi star representative. Okay. So the area of this rectangle of the sample is, well, there's the height times width. Okay. And you see, as I mentioned, and I showed you in Maple, you can pick uh, any representative. Actually, you can pick left hand, right hand, or even choose a random points on that interval. Okay, so that's the our sample. The third is you sum it up. Okay, so you get uh, say the approximations. So the whole area is approximated by this sum. Say sum according to the partitions. Okay, I just write this one with the subscript P partition. So this is the Riemann sum. Okay, so this is the approximation of the area. Area of the area under the curve. If f of x is non-negative as this one. Right? I meant to write to draw something below also the x-axis, but somehow forget to do that. Okay. And the last one is take limit. And the area, if you get this one, will be the limit of this Riemann sum as the size of the partitions gets finer and finer, goes to zero. Okay, take a look at it. So we call this the if limit exists. Regardless of the choice for partitions and representative. Okay. All right. So I'll give you some example to somehow highlight some ideas of the what does it mean by regardless of the choice of partition and representative. Okay. So let's see uh, this one examples. Uh, the Riemann sum depends on this one example. Give you an idea that the Riemann sum which depends on the representative. Right? So let's think about this function now. Say one if it is a x is rational, one half if x is irrational. Okay, so x between 0 and 1. Okay, so just restricted to 0, 1. So let's compute the Riemann sum. So if you draw the picture, that's easy enough. This is 1/2. Okay, so you get something like looks like this. So x rational is 1. Here you have a if irrational, then this is 1/2. So if the value is not here 1/2, then the value should be here 1. Okay, so both are what we call porous. All right, so this one. So we first we do the partitions. Let's say 0, x0, x1, x2, then xn. Okay, so the partitions. But xn equals b, l equals 1. Okay. All right. And so let's just take there. Okay. That's the all right. Pick a pick samples. Okay, so a sample should be um, delta by x. Okay. The thing here is that, all right, so if our representative is rational, then it's just x. Okay. If the representative, if rational, otherwise, that's 1/2. If is irrational. Okay. So you get a little bit confused because sometimes it's rational, sometimes it's irrational. And the thing here is that for every here, there is a rational point, there is also irrational point. Right? So at every interval, there is rational, there is, and they can be representative. Okay. So now, if you do the summations, so the height is 1 or 1/2, depending on the representative. Okay. So the Riemann sum, so first case, uh, all the representative are rational. Okay. So the Riemann sum is just all 1. So what you get here is that just summing up delta x. Okay. But remember that when you sum this up, you have a telescoping sum, because this is telescoping sum. So you get endpoints. Yes. Okay. And the second is the case all representative are irrational. So in that case, our Riemann sum is 1/2. Okay, you take 1/2 out. This is 1/2. Okay. Okay. So the take limit. Well, the limit kind of confused because what kind of representative you use? If you use rational representative, then you always get 1. But if you use irrational representative, you get 1/2. So the limit depends on the representative. Take limit depends on representative. So rational representative give you this limit. Just this is always 1. So just 1. and irrational representative if you this Riemann sum. Okay, so clearly they are not the same. So this is an example when you don't have a limit. So limit depends on the representative. Okay, so this is the case. Questions? Okay. All right. So when the limit exists, okay, exists, it is called definite integral. Okay. So this is the definitions. Definite integral of f from a to b on the let me just writing this verse. Limit of 0 of the Riemann sum representative there. Okay. So this is the definite integral of f on the interval AB. Oh, sorry, this is limit exists regardless of the choice uh, for representative. Okay. And definite integral. Okay. More thing. And f is called integrable on. Okay. So this particular case, like this. Let's see, look at this one. One if x is rational, zero if x irrational. This is not integrable. On 0, 1. So that's one example of something that's not integrable. Okay, because it's depend on the representative. All right, any questions so far? Okay, so the notations integral looks like an S anyway. This sum, there is a limit of that sigma. So remain rather mysterious here is how the definite integral relate to indefinite integral. So what we have as a what we call this anti-derivative. So we'll cover that in a moment, just quickly, how those two relate. And this is, say, you can say this is the peak of what we have in calculus 1, actually. So everything in the calculus one centered around the fundamental theorem of calculus. All right, questions? Okay. Let's see here. Just see. Just okay. Can you see the from the book now from Purcell? You can see this is definitely Crow.
Again, see the book, sir.
Yeah, see. Okay. Definitely Crow. All right. So what it means pictorially, geometrically, that's area. Area under the curve, not really under the curve, but area if the function is above the x-axis, then it is really the area. Okay. So the book give a term here is that sine area. Okay, sine area because this can be positive or negative. Because we know area must be positive. But if something is below the x-axis, and then the integral should be negative. So this is the negative area. So this is why we call it sine area. This is the definite integral. All right, some properties of limit that we will use it later. Okay. I would like to show you something else here. And sometimes we write something like this. This is the norm of the partitions goes to 0. Just call something like this. Okay. So the limit as the partition gets finer and finer. Finer means it's really okay. Fine versus coarse. Okay. If you grind coffee, then you have grind it coarse or fine. So this is good. Now I want you to distinguish with this one here. N goes to infinity. E from 1 to n. So how these two are distinct here? Okay, we will use this one. It's slightly different. Okay. Oh, where are my screen? Okay. Can you see the screen back now?
Yes, sir.
Okay, all right. So what is the difference? One note stuck. Kill is off first. One note. There, and ask. Okay, and that is sorry. Let me just stop share first, and then let's do a little bit. Is the difference. So so the norm of p gets to 0, meaning that uh, so this is the minimum, right? If this is goes to 0, okay. So the made a big mistakes. Uh, the size for the partition P should be the max, not the min. Sorry. So the largest, you what you see is they always observe is the largest. Everything else is smaller than. Now, I'll repair the notes later, revise notes. Okay. If the max is goes to 0, so everything else goes to 0. Everything gets smaller and smaller. So all delta x get smaller. Goes to 0. And if it is smaller, all. Yeah, that means you gotta have lots and lots of uh, many of this. Okay, that means n goes to infinity. So if norm of p goes to 0, that means n goes to infinity, right? But the other directions, is that true? If n goes to infinity, then it's 0. No, just observe this example. So you have, say, partition 1. Partition 1, you have only this. Okay. So the norm for partition 1 is, let's see, this 1/2, 1/2. In the second partitions, we divide this the two parts. So say this is P2. And the norm with P2 is, let's see, this is still 1/2. And here is 2 and 3. Okay. And then the next one should be, say, this one. 0, 1/2, 1, 6, 8, 7, 8, 5, 8. Okay. So this P3 has a size still largest. Largest is still 1/2. But n equals, let's see, so 1, 2, 3, 4, 5. Yes, there's 5 now. Okay. So you keep doing this. Keep on doing this one. So 1/2. So just keep refining this part. Okay. So keep refining this part. So you will have that. Say this is the ends. What you call partitions. It's still 1/2, but here you have uh, n is large. Okay, so you see that in this example, you see n gets larger, but the p still 1/2. So it doesn't go to 0. It's go to 0. Okay, see there are two different things. So we use this one. Okay, so what are integrable functions? So let's see. Just show you the theorem. What function are integrable? Okay, so just pick this up. Let's write this down. Okay, so this is what are integrable. Continuous function is integrable. Uh, well, it may have discontinuity, but finitely many. In particular, f continues a whole interval, then it is integrable. Okay, so as long as uh, you have integrable functions, then it does not depend on the partitions. Then you'll get the limit. All right, so polynomial, sine, cosine, rational functions. Okay, this is the thing that we will use. Okay. All right, I think one example here. Okay, so that's example. Compute, delete. Example. Okay, so this is a polynomial. Polynomial is continuous. Okay, polynomial, quadratic, hence continuous, and it is integrable. Okay, so the integral does not depend on the way you partitions. Okay, so the limit does not depend on partitions and choosing representative. Okay, so just let's do the, in that case, we can choose the most convenient one. What is most convenient one? The most convenient one meaning uh, uniform partitions with a uh, nice endpoints. What mean nice endpoints? Okay, so let's see. Okay, what we okay, divide into n, so x0. This is 1n, 2 over n, 3 over n, 4 over n over n. Okay, so this our partitions. Our partitions is 0, x, that xi is I over, okay. And we choose the representative equals, say, same thing here. So this I over n, so right endpoints. Okay, right endpoint. Let's compute this. This partition. Our sample is going to be it's the width is 1 over n. The height is f of I over n. Okay, so then this give you minus 5. Okay, plus 7. Is that our functions? Yes. Okay, so that's the sample. Third, Riemann sum. So the Riemann sum is because this is n, so sorry. So you can say I from 1 to n, f I over n times delta. So this gives you 1 over n times, okay, because we have the formulas of that sigma notations. Okay, so we take this one friend out. Okay, and all right, look at this one. here is 1 over n squared, sum of I squared. And takes out 5, and then this n from here. Okay, and this is just 7n. Okay. Okay, so what we have here, so just 1 over n cubed. We know how to compute this. This gives you uh, n plus 1 to n plus 1. That's the formula. Okay. And then here we have n squared now. This is I plus 1 plus 7. There we go. So this is the Riemann sum. And then the last thing is the take limit. Okay, so this limit here is 1, Riemann sum. Yeah, actually, this will be the same because this f is integrable. Then it is the same as this sum. Okay, so you get something like this. This cube. So this is 1/6. Oh, sorry. This n cube here and 2n cube. So that's 1/3 from here. From here you get this should be n. That's where so 5/2. Okay. Okay. So then that's the value of the integral. Okay, so all right, so the last thing is that to compute definite integral is very laborious. Okay, so it's a lot of things you need to compute, and you depend on the sigma formulas. So without sigma formulas, you won't be able to compute the integrals. Okay. So, calculating definite integral is a laborious process. So the questions now is that, of course, can we simplify the computations? Second, how definite integral relate to indefinite integral. Okay. So this points out to what we call fundamental theorem of calculus. Okay. Okay, we'll cover this tomorrow then. So we end this additional sessions. at this point. Okay, questions? Questions? All right, then I'll stop share, stop record first.